Hi, and welcome back to Engineering 255 Statics. This is the second video of the Chapter 5. Chapter 5 is about equilibrium of a rigid body. In the previous video, we tell you when you dealing with the equilibrium that is not a point, that you not only consider about the summation F equal to 0, you also need to consider about the moment. Because if you have a rigid body, you apply a force at a different location, it will make the rotation differently. For a single point is not the case because a force applied to a single point is not going to make it rotate. We also show you the importance of the drawing free body diagram. And here we are going to discuss about how do you write an equation of equilibrium to solve the problem. We're also going to look at an important concept called the 2 force member and 3 force member. So the objectives of this section is to show you how you can apply equation of the equilibrium to solve the unknown, and also how do you recognize a 2 force members. To start with an application so you will understand what we were talking about, we see this picture before. Point A is what? Is a pin. So what is the function of the pin? Pin would allow that you give support in the X and Y direction. However, it will allow the object to free rotate. If this one can be free rotate about the point A, then you will not have any of the reaction force at point of A. This ramp here has a weight, so if you wanted to draw a free body diagram of this ramp, then you certainly need to consider about the weight of the ramp. What else do we need to consider? Well, certainly there are cable, there are pin, they all will create some reaction force when you isolate the ramp. So what is the equation of equilibrium for a rigid body? For two-dimension free body, then you have a net force and also the net moment acting on the body are zero. In terms of the equation, this is the equation for two-dimensional condition. We'll look at three-dimensional condition later. When you do a summation moment, you need to know that the moment is the moment with respect to some reference point. So you always put the reference point at the lower end so you would know where that you refer to. This is needed because when you calculate the moment, you need to know the lever arm. All right, so the next one I wanted to talk about is the idea called the 2 force members. And there's another so-called the 3 force members as well, but we will focus on the 2 force members here. If we need it, then we would define the 3 force members, or you can read the definition of that from the textbook. In the later part of this course, you're going to solve a problem about truss, which is like a bridge. And most of the truss are composed by 2 force members. A 2 force member simply said the member only had a force applied to 2 endpoints. And this member doesn't have to be a straight member. So like this one here is a curved member. However, you only apply force at the A and B, so those are 2 ends of this object. Now, this could be extended even though that you apply point at here, that is still fine, as long as you can only have 2 force applied to both different ends. So why this one is important? If you apply force to the two force members, then the resultant force at A and B must be equal in magnitude and act in the opposite direction along the line joining points A and B. What does that mean? That simply means this case right here. If you only have these 2 points that will apply force to this 2 force member, these 2 force will stay along the line of the A and B. So you connect A and B point, then the force will go along this line. And the force will be equal and opposite direction. Then it will be like a couple, but the couple is not a couple, because if this is a couple, it's not going to create any of the moment, right? Because there's no distance between these 2 couple force. Let's look at some of the examples, some of the real example you can look at here. In this yellow color device, you have like an angled bracket here. It has end of the A and end of the B. These 2 connect to some object, right? So when you connect to some of the object, when you isolate this piece, you're going to have a reaction force at the A, you're going to have a reaction force at the B. And this, if this one is a pin, then you're going to have a reaction force at the X direction, Y direction. Same thing over here, X direction, Y direction. And that means you're going to have 4 different reaction force. It's very complicated because you have 4 different unknown. Then you want to solve it, you need 4 equations. However, if this is a 2-dimension, you only have 3 equations maximum can solve the problem. However, if you look at this piece here, there's nothing else of the place that you apply force to this angled bracket, because you only apply force at point A and point B. Therefore, if you wanted to draw the force, then the force will be go along this line right here from A to B or B to A. It's going to be along this line. So if you think this is going to be a force going to this way, then you're going to have a force going to that way at both ends, because they have to go along this line. They have to have the same amount of the force. Similar to that one, this red, I don't know, like a lift device here, and you have a hydraulic lift right here, and you have 2 ends, A and B. Again, this pin here and this pin here is the end point of this hydraulic device. And this will be also treated as a 2 force member, and then you can simplify this problem by summing their force at that specific direction. Now let's look at what is the step to solve a 2-dimensional problem and to solve a 2-dimensional equilibrium problems, right? The first step is actually to select the coordinate, because in the real situation, it doesn't have to be horizontal and vertical. It could be an angle direction, depends on the device shape. So you want to select the proper XY direction so you can find out what is the angle of your vector. The second, which I think is the most important thing, is to draw a correct free body diagram. When you do a free body diagram, you not only just isolate the object, you also need to identify what are the forces acting on the object, including the thing that we mentioned in the previous video, supporting force, supporting reactions. If you have a roller, it's going to be a normal force. If it's a pin, you have supporting force X and Y. If that is a fixed end, you have both supporting force and a moment. And then you apply the equation of equilibrium, which is the summation F equal to 0, summation Fy equal to 0, and summation moment at a point equal to 0. So that is the condition of the equilibrium, and then you use this equation to solve the problem. Some important notes are here, just try to remind you, well, if you want to solve a unknown, if your unknown is more than the number of the equation that you can come up with, this is called an indeterminate situation. And then simply just said, you cannot solve it numerically. You cannot get a numerical answer because you don't have enough equation to determine the exact value of the solution. You need to have enough of equations. If you have 3 unknown, you have to have at least 3 equations. And where do you start the calculation? You sometimes can simplify the solution. So this just give an example, like if you have 2 unknown vertical forces and 1 unknown horizontal forces, then you solve summation f of x equal to 0 first, right? Because horizontal, you only have 1 unknown. So if you write this equation, you solve the unknown directly. It will just help you to solve the problem directly and easier and faster. And if you got an answer, which answer is negative value, that simply means that you assume the direction of the force or the moment is opposite to the exact direction. Then you just simply flip the direction in your picture. That's the correct direction of your solution. Okay, now it's the time that we look at some real example to show you complete solution for a case of the rigid body equilibrium. So you're given a 4,000 Newton load at point B, and the beam is supported by the pin A and C. Now here, this is a key point. This is the pin, and there's actually 2 pins, one at A, one at C. The load is at the end of this beam here. And you have this one is a pin, and this one is also a pin. Actually, this point is a pin as well. Do we have a 2-force member? Would you think a CD is a 2-force member? And the answer is yes. What about A and B? Would A and B a 2-force member? And the answer is no. A to B is not a 2-force member because you have a force at A, you have a force at B, but you also have a force at the C. So this is not a 2-force member. This is a 3-force. Okay, so 3-force is going to be different than a 2-force member. So if this is a 2-force member, that means the force at here is going to be equal to the force at here is going to be along this line here. So I can simply assume the reaction force at here is going to be go along this direction. All right, so let's just look at how we solve this problem completely. First, we're going to assume the x and y direction. In this case, is very like a typical horizontal and vertical, so we can set up the coordinate, just go in the regular way that we set up the coordinate x and y. And we just show you what is the 2-force member, right? So the 2-force member is going to be the C and D is a 2-force member. Then you're going to draw a free body diagram on this bone AB. Then we can apply the equilibrium equation to solve the problem. And so when you do a free body diagram, this is the free body diagram. This is a 2-force member, so the force is going to be going along this bar here. So you don't need to worry about x and y because you know exactly the direction of the force. So where this is F of CD, and it's going to be applied to the point of C. For point of the A is a pin, so you have two supporting forces, AX and AY. You're going to draw these two. And you also have an external load, which is 4,000 at the point B. So this is the point B at here. If they give you the weight of this boom at here, then you have to apply the weight at this point as well. Okay, so that's something that you need to remember. So once you have all these together and you are ready to solve the problem, you just write down the equation of equilibrium. So summation of fx, summation of y is very simple, and you can simply just do that by yourself. But to solve this problem, the easiest one to start is actually to do the summation of the moment. When you do a summation of the moment, I normally will pick the reference point where you have most of the force acting on that point that you don't have the result, or you don't have the value for that. And that is why they choose the point of A, because when you choose point of A, AX, AY will contribute no moment at all. So you don't need to worry about these two. All you need to do is to look at FCD and also this force at here, how much moment it will create to this point, and it will be sum equal to 0 because this object is not rotating. It's not rotating, so the summation of the moment has to be equal to 0, and A is the best point to start with. And when you do that, you look at the force at the B, that is equal to this much of the moment. This is a clockwise, so we put negative at the front. And this one, FCD, how do you do that? Well, this is what we did in the chapter 3, or maybe even in the chapter 2. You need to find the perpendicular distance from this force to the point of A. Another way to look at that is to decompose this force into two different components. This is one component, and this is another component. And you look at each one of the components and how much of the distance from this component to this reference point, right? Or another way to look at that is that you can also extend the force and try to find what is the lever arm. So this is the lever arm. This is the distance you need to multiply to get the moment. And this is going to be 90 degree. This will be 45 degree. Right. And so if this one is 1.5, which is hypotenuse, this is the 45 degree. You can use the law of the sine. Or you can simply just say, well, the sine 45 degree is going to be equal to the cosine 45 degree, because they are going to be the same. And it's going to be this distance divided by 1.5. Right, this is the lever arm. And so 1.5 times sine 45 degree is your lever arm, is this distance right here, and you multiply with FCD, that is the moment, and that has to be equal to 0. And you start this equation because when you use this equation, you will find out, you can find out FCD directly because there's only one unknown in this equation. After that, then you can simply just sum the force. You certainly have to decompose FCD into FCDX, FCDY, and then you can find a solution. And you can see that we have a negative value right here. That just simply tells you when you assume the AX direction to the right, the actual direction should be go to the left. And which makes sense because if this force is applied to this direction, you want to balance this direction of the force, this has to go to the left. And if this one goes to the direction to right upper corner, and this one goes down, how do I know this is a positive or negative? Well, unless you solve it. So you solve it, you find out AY is negative, that means the actual AY is going down as well. And that's how you solve this problem. Well, I hope the example give you some idea. We're going to solve more problem when we have the face-to-face lecture. And please start to work on your homework to get some more practice. This chapter is not very difficult, but it's put emphasis on the free body diagram, and practice some of the problem will help you to understand the concept of this chapter. This is the video 2. We're going to see you in the next one.